Hello friends, here in this video we will see a problem on calculation of shear stress for a T section, and for that here we have a question. Whatever is given here I will write that in the form of data. Now a beam AB supported at its ends has a span of 2 meter. So span means the length of the beam is given, it is 2 meter, so 2000 mm, and it carries a UDL of 200 kilonewton per meter over the entire span. So it means that here, if I can explain it with a diagram, the beam is supported at its two ends, I'll call it as end A and B, and then it carries a UDL over this beam. There is a uniformly distributed load whose intensity is given as 200 kilonewton per meter over the entire span, means over this entire length. Then the cross section of the beam is T section. So if we look from the side, then the cross section is T, and for that T section the dimensions are given, having flange width 125 mm. So flange width is 125 and thickness is 25 mm. Similarly web thickness is 25 and overall depth is 200 mm. So all these things I'll denote it directly onto the diagram. Calculate maximum shear stress, that is tau max, and maximum shear stress in the beam, and draw shear distribution diagram. So this is the question we have. Now let us try to get the solution to this problem. Now in the solution part, first I'll say that since the beam, or I'll say the given beam, carries UDL over its entire span, so therefore reaction at each end will be same. Means when we are having UDL over the entire span, then that UDL would be converted into point load, and that point load would be shared equally by each of the supports. As we can see here, at A I'll call it the reaction as RA, at B the reaction as RB. So here I'll say that therefore reaction RA will be equal to RB, and that will be W into L divided by 2, because W is the intensity of UDL. When we multiply it by the capital L, that is the span, we convert it into point load, and that we would be dividing into two halves, that is the load is shared equally by each of the supports. So therefore RA is equal to RB, and that will be W value is 200, it is given kilonewton per meter, into the span is 2 meter divided by 2. So therefore RA is equal to RB, and it comes out to be 200 kilonewton. Now I'll say that since in this case here we are solving the problem on shear stress, so in shear stress this force which we are getting RA, RB, these are called as shear force. So therefore shear force, it can be denoted by S or it can be denoted by F, that is nothing but the reaction, which is 200 kilonewton. Now after getting the shear force, the next thing is, since it is given that we are having a T section here, so I'll draw the diagram for that T section. Now here I have drawn the T section. I'll mark the dimensions over this. Here is the flange, here we have web, So the cross section of the beam is T section having flange width 125 mm. So the width of the flange here is 125 mm. Next, flange thickness is 25 mm. This is the flange thickness. 25 mm. Then web thickness is 25 mm. And overall depth is 200 mm. So this is the overall depth, 200 mm. Now, first of all, once I have marked all the dimensions on the T section, I'll need to get the value of centroid here. That is, centroid needs to be located. As I can see, this T section is symmetric about the vertical axis or y axis. So centroid will lie on this axis. This is the y axis. So therefore, the distance of this y axis from the origin, that will be nothing but x bar. So I'll say that therefore x bar is directly half of 125. So therefore here we have x bar as 62.5 mm. Next, we need to calculate y bar here. So I'll say that after this, therefore y bar is equal to a1y1 plus a2y2 upon a1 plus a2. Keeping this as equation 1. Now this web portion, I'll keep it as section 1 for us. Flange will be the second section. So area 1 will be, therefore area 1, that will be, here the width is 25, so it is 25 into the depth of this web is 200 minus 25. This is the depth of the web, which is 175 mm. So 25 into 175. So area 1, it comes out to be 4375 mm square. So now, after getting area 1, area 2 will be equal to, for this second section the width is 125, depth is 25. So this area comes out to be 3125 mm square. Now after getting these areas, y1 will be, now y1 is the location of centroid for the first section, so it will be at half of 175 and it is 87.5 mm. Next, y2 is the location of centroid for the second section and its centroid is located at the x-axis, which is passing here. So the distance of this x-axis from the bottom will be 175 plus half of 25. So it is 187.5 mm. Next, I'll say that therefore put all values in equation number 1. So I'll put all the values here. So we have y bar is equal to, area 1 was 4375, y1 87.5 plus area 2 3125 into y2 187.5 upon area 1 plus area 2. So therefore y bar value comes out to be, it is 129.17 mm, 0.17 mm. This is from bottom. Now, after getting the location of y bar, I locate the x-axis for the complete section. This is the x-axis of the complete section. Its distance is 129.17. mm from the bottom. Now once we have x and y axis, here is the centroid for the complete section. Now if we look into the question, here we have to find out the maximum shear stress, and for that maximum shear stress we even require the moment of inertia. The moment of inertia about the centroidal x-axis. So the next thing would be I'll calculate the moment of inertia. So after reaching here, I'll say that now since mi about x-axis, that is moment of inertia about x-axis for a t section, that is given by Ixx is equal to Ixx1 plus Ixx2, keeping this as the second equation. Now I'll calculate separately Ixx1, Ixx2. Ixx1 will be I1 plus area 1 into h1 square. Now what is I1? Here I1 is the x-axis for the first section, which will be at half of 175. So this is the x-axis. I'll call it as axis 1, located at distance y1, which is nothing but 87.5 mm from bottom. So about this axis, which is 1, the moment of inertia would be, since it is horizontal, so that will be I1 is equal to BD cube by 12 plus area 1 is B into D. H1 is the distance between the two x-axis, that is x-axis of section 1 and x-axis for the complete section. This distance is nothing but H1. Here we have H1 distance. So that will be 129.17 minus 87.5 whole square. So putting the values here, for the first section width B is 25 and depth is 175. Area we have found out, it was 4375 into this bracket. So here I am getting the value of Ixx1. It comes out to be 18.76 into 10 raised to 6 mm raised to 4. Now similarly, I'll calculate Ixx2. That will be I2 plus area 2 into h2 square. Now if we look into the problem, the x-axis for complete T section, it is passing at xx from this xx axis, and the x-axis for section 2 is passing here. So there is some distance between the two axes, and this distance is h2. So here we need to know what is this h2. H2 will be here, as we can see, from 200. If here this is 129.17 mm from bottom, so I'll say that therefore Ixx2 will be, first of all, I2 is nothing but BD cube by 12, area 2 is B into D, and here we have h2 square, and this is by parallel axis theorem. As the two x-axis, they are not passing through the same line, so we are using parallel axis theorem, as we have used in the first case as well. Now therefore Ixx2 will be equal to B and D values for the T section. Here for this flange, B is 125, D is 25, so 125 into 25 cube divided by 12 plus 125 into 25. Next, H2 is nothing but 187 0.5 minus 129.17 square. So from this I'll get the answer of Ixx2, and that comes out to be 10.795 into 10 raised to 6 mm raised to 4. So here I have the value of Ixx2. Now after getting the value of Ixx2, the next thing would be putting these values in equation number second to get Ixx. So therefore put Ixx1 and Ixx2 in equation number second. So I'll add the values. Therefore Ixx is equal to Ixx1 18.76 into 10 raised to 6 plus Ixx2 10.795 into 10 raised to 6. So therefore Ixx value will be, it comes out to be 29.56 into 10 raised to 6 mm raised to 4, and this is nothing but I. Now after getting this, here in the question it was mentioned to calculate maximum shear stress. So I'll say that for given T section, maximum shear stress will be at the neutral axis. So now for given T section, maximum shear stress will be there at the neutral axis, and that maximum shear stress is denoted by tau max. Formula is F A y bar upon IB Now sometimes this F, which is called as shear force, can also be denoted by capital S. Capital S or F, both are same here. So next, now tau max, since it is there at the neutral axis, so to calculate that we require the area from the bottom only up to the neutral axis, because we want the stress at neutral axis, so we have to consider the area below the neutral axis as we are taking the reference from bottom. So the area will be 129.17, that is height into width as 25. So here I'll say that, keeping this as equation number third, I'll say that capital A is 129.17 into 25, that is the area of the web which is below the neutral axis, and that comes out to be 3229.25 mm square. Next, y bar is nothing but the half of the height. Height is 129.17, so half of that is y bar, and it is 64.59 mm. Then I'll put all the values in equation 3, and for that I is the value here. B, since we want to calculate the stress at the neutral axis, so width B will be the width of the web, because at the neutral axis we have web, so this much width we have to take, which is 25 mm. So I'll say that, putting all values in equation number third, so we have tau max is equal to, now F is nothing but the shear force we have calculated at the start of the problem, and that shear force was 200 kilonewton, so that becomes 200 into 10 raised to 3 Newton. Next, area, capital A, here we have found out, so I'll put the value. Then y bar value is 64.59 upon IB. I is 29.56 into 10 raised to 6. and B is 25, the width of the web. So on calculation, I'll get tau max value as it is 56.44 Newton per mm square. This is the answer. I'll call it as our first answer. Now, if we look into the question, here the question was to calculate maximum shear stress. We have found out the value in the beam and draw shear stress distribution diagram. Now for this shear stress distribution diagram, we require stress at other points as well. So after this, I'll say that therefore the first thing would be, once I have calculated the maximum shear stress, now I'll find out shear stress at the junction of web and flange. So to calculate the shear stress at the junction of web and flange, I'll call it as tau 1 and the formula will remain same, Fa y bar upon Ib. Now, in this case, since I am calculating the shear stress at the junction of flange and web, so when the flange and web they are meeting, here is the junction and even here I can say that this would be the area. So area I have to take it as the area of the flange and not the area of web. So I'll say that here A is equal to 125 into 25, which is 3125 mm square. 125 into 25. Here I have got the value of area. I is constant. B, we have to take the width as the width of the flange, which is 125 mm. I'll call that as B1 and B1 is 125 mm, which is here. Next, y bar. After this, the y bar value will be, I'll calculate y bar here itself. Y bar will be, now y bar means here we want to know the distance between the neutral axis and the x axis for the second rectangle, that is this height h2, and it is 129. It was from 200. First I'll subtract 129.17. So 200 minus 129.17. So once I subtract from 200 this distance 129.17, I am going to get this total distance, and from this total I'll subtract half of 25 so that I get this distance, which is h2. So here we have, after this, minus from this 25 by 2. So therefore y bar value, it comes out to be 58.33 mm. Next, I'll put all the values here. So calling this as equation 4. So therefore put all values in equation number 4. Hence we have tau 1 as equal to, now F, as we know, it is 200 into 10 raised to 3. Area we have found out, it is 3125 into y bar is 58.33 upon I into B1. I was 29.56 into 10 raised to 6 and B1 value is 125. So from this I'll get the answer of tau 1 and it comes out to be 9.87 Newton per mm square. Next, after this, I'll calculate another value of shear stress, and that value will be at this location. Previously the shear stress which I had calculated, it was here Now I'm calculating the shear stress at this location. So for that I'll use a special relation, that now using the relation of shear stress and corresponding width. So using that relation, so now here I am using the relation that tau 1 upon tau 2 is equal to inverse of the ratio of width, that is b2 by b1. Here a very important conclusion I am using, that shear stress are inversely proportional to the width, that is where the width is minimum, shear stress will be maximum. So from this ratio I can say that therefore tau 2 will be tau 1 into b1 upon b2. So tau 1 is 9.87, b1 is the initial width which was 125, b2 is the width at the junction which is nothing but width of web 25. So from this I'll get tau 2, therefore tau 2 value comes out to be 49.33 Newton per mm square. Now once we have got all the values, now we can draw the stress distribution diagram as it is asked in the question. So here I'll write down shear stress distribution diagram. First I'll draw that T section which was given in the question. Now here the T section was given and we have found out that the neutral axis was located at a distance of, it was 129.17 mm. So I am marking all the dimensions here first. Now after marking the dimensions here, now I'll plot the shear stress variation. And for that variation, first I need to draw a vertical line. Then the neutral axis would be extended by a light line. After that, the junction of flange and web would be projected light. Now, at the extreme corners, the shear stress value is 0. So tau is equal to 0. Then at the neutral axis the shear stress is maximum, so here I'll write down tau max, value was 56.44 Newton per mm square. Next, now at the junction where the flange width is 125 mm, there means here at the junction, here the stress value we have got it as tau 1 which was 9.87 Newton per mm square, tau 1. So the nature is such that here I'll get the value tau 1 as 9.87 Newton per mm square, and joining them, so from 0 the shear stress will go on increasing and it will reach up to 9.87 Newton per mm square. Then after these points we had calculated the shear stress at the inner junction taking the width of the web which was 25 mm. So here at width web is equal to 25 mm, the stress was 49.33. So when area decreases, as we can see here, stress will increase. So from 9.87 it will go on increasing up to a value which is 49.33 Newton per mm square, and then it will reach a maximum value here, and after reaching the maximum value again it will go on decreasing such that it becomes 0. So this is the shear stress variation as we can see here, and with this we complete the question.